Hi everyone, I'm Eulalia, a dual Ph.D. student at the Institute of Physics of University of Tartu, Estonia, and at the Laser Research Center of Vilnius University, Lithuania. Today, I'm here to talk about our recent research work done on a novel computational imaging technique titled Spatio-spectral correlations in interferenceless coded aperture correlation holography with Vortex speckles, which has been published in Nature Springer, Applied Physics B. As some of you may know, interferenceless coded aperture correlation holography, abbreviated as ICOACH, is a computational imaging method that enables three-dimensional information of an object to be obtained under incoherent illumination and without the need for two-beam interference. Initially, ICOACH was implemented using a scattering mask, which scatters the object beam, producing a chaotic distribution at the sensor plane. In posterior studies, certain levels of engineering were performed even with a scattering mask to control scattering, which are referred to as quasi-random phase masks. In recent studies, ICOACH has also been implemented using a wide range of coded masks that generate spatially structured beams, such as Bessel beams, Airy beams, or Laguerre-Gaussian beams, and even sparse arrays of such structured beams that do not interfere with each other. In this study, we proposed and demonstrated for the first time ICOACH using a phase mask that generates vortex speckles. We have designed a mask that generates beams with a combination of two properties, with random values assigned, a linear phase and a spiral phase. This results in beams propagating along different directions due to the linear phase and carrying orbital momentum due to the spiral phase. Their interference in the sensor plane produces a chaotic pattern, but unlike regular speckle patterns, these speckle patterns formed by self-interference have unique and diverse intensity distributions, and differ from regular speckles in their composition as they contain orbital angular momentum. It's because of these reasons that we have named them vortex speckles. Our study has focused on testing the imaging characteristics along 4D, 3D space, and a spectrum. And additionally, we have studied one phenomenon discovered in ICOACH, the so-called depth wavelength reciprocity, which we'll present in more detail in a few moments. The study was divided into two phases, first the simulation studies and later on the experimental validations. To generate vortex speckles, both in the simulations as well as in the experiments, we designed a coded mask using the transport of amplitude to phase based on the Gerbeck-Saxton algorithm, abbreviated as TAP-GSA. This method allows to encode multiple spiral and linear phase components into a single phase-only mask, which we refer to as the vortex ensemble generator. Let's start by explaining the simulation studies. The simulations were carried out to evaluate the 4D imaging capabilities and depth wavelength reciprocity behavior during 4D correlation. These simulations involved reconstructing objects located at different depths and illuminated with different wavelengths. The reconstruction was done using the Lucy-Richardson-Rosen algorithm, an iterative algorithm consisting of forward convolution and backward nonlinear correlation. Our results demonstrated that accurate image reconstruction is only possible when the point spread function, abbreviated as PSF, used in the reconstruction matches the depth and wavelength of the recorded object. When a different PSF is used for reconstruction, the object information is distorted, and the reconstruction is no longer recognizable as the object. We also explored a phenomenon termed depth wavelength reciprocity, which stands for the characteristic feature of Fresnel refraction in which a spatial aberration can be compensated with a spectral aberration, and inversely. This effect was discovered in ICOACH in previous studies and was used as an advantage in recording the PSF library. Nevertheless, this reciprocity between depth and wavelength leads to an ambiguity between these two properties and can be undesired in sensing applications, as it's not possible to certainly know the position and wavelength of a specific point of the object. The simulations done on depth wavelength reciprocity when using vortex speckles showed that as the number of vortex beams increases, this depth wavelength ambiguity is suppressed, and when the number of beams reached around 50, the ambiguity is removed. Moving on to the experimental part, we validated our simulations through two experimental setups. First, we implemented the design mask using a spatial light modulator, abbreviated as SLM, allowing us to display the phase masks dynamically. We first recorded the point spread functions by placing a pinhole to act as a point source. We used red and green LEDs to illuminate it, and we recorded the resulting intensity pattern at different depths. After recording the PSF, we replaced the pinhole by test objects and recorded the resulting intensity pattern at the same depth and wavelengths. Following up, we fabricated physical versions of the Vortex ensemble generator using photolithography. This included both amplitude-only and phase-only binary masks. The fabrication process involved spin coating photoresist on glass substrates, UV exposure, developing and drying, and in the case of the metallized one, metal deposition using electron beam evaporation. In both setups, we recorded PSFs and object intensity distributions under identical conditions, and reconstructed the images using the Lucey-Richardson-Rosen algorithm. The results confirmed the system's ability to retrieve object information only under matching conditions, proving the exceptional 4D imaging capabilities of ICOACH using vortex speckles. Our findings can be summarized as follows. High fidelity for the imaging was achieved using vortex speckles with strong discrimination between different depths and wavelengths, and it has been proven that it can be implemented both with the use of an SLM, which allows tunability of the mask, as well as with physical masks, fabricated via photolithography, for a more compact setup. The imaging resolution improved with the number of vortex beams. Increased vortex beam density led to the suppression of the depth wavelength reciprocity property, resulting in high discrimination of information from different depth or wavelengths, which demonstrates potential for optical encryption and security applications, as the reconstruction is highly sensitive to the exact imaging parameters. In conclusion, we have demonstrated a new implementation of ICOACH using vortex speckles. The combination of a structured light, advanced phase mask design, and robust reconstruction algorithms enables high resolution, 4-dimension imaging without 2-beam interference. We believe that ICOACH with vortex speckles holds significant promise for applications in digital holography, optical sensing, and secure imaging. Future work may explore its use in optical communication systems, particularly for detecting phase and topological charge of vortex beams. Thank you for your attention. We hope you enjoy exploring this research work with us, and please contact us for any doubt. See you in the next video!